Right, okay. For those that are here live, well done you on a Friday afternoon. For those watching in the recording, the first thing I want to just quickly show you is if you are having any logon registration issues with the website. So what I've done here is obviously I've opened an incognito window so that you can see what this looks like. Do make sure that you are opening this link in a proper browser, i.e., not, when your phone sometimes opens it off the email and it's not actually in the browser, it's just like a layer on top of your email or on top of the app that you're using. Make sure you're in, it should work in any browser, but make sure you're in one. Because I'm in an incognito window, you can see it says login register at the top. And I've just realized I'm also just going to check. There we go. Making sure I can keep an eye on the chat and anyone else coming in. Um, So if I click any of these lessons, it's going to obviously tell me that I'm not logged in. Don't click on take course. I've no idea what that button's for. It's very annoying. It doesn't seem to take you anywhere. Okay, let's just let someone else in. So instead of clicking on that, click on sign in. I've already set up a extra account, apart from my obviously user account because it's my website, at ckchemistry.co.uk. The password is whatever you chose, or register and choose your own password. Ignore any passwords that I've sent via email. So pop that in and press login. And then if it takes you anywhere else that you don't want to be, then at the top of the website, it's not there. I see. Okay, if you ever go back to the website, so for example, I don't know, you have accidentally gone back and lost it. If you click on my courses, then you should still find it here. So I'm actually, you see at the top it says log out there. That shows me that I am logged into the website. And so then I can go back to that and find whatever lesson I want. The reason it's only showing day one, day two, day three is because I have at least managed the technology enough to have it so that the different days come up at different times. So that's all that is. Okay, let's get on to some chemistry. I've had a question about one of the multiple choice questions in about oxidation states. And the formula from the name and why that's the correct formula for potassium bromate, or how you would work that question out. So we've got potassium. Obviously, potassium is potassium. In a compound, it can only be +1. So that is a fixed oxidation state element. It's in a salt. Bromate is an ion containing bromine and oxygen. So I know that much, but that doesn't help me because they're all there. The 3 is going to refer to the oxidation state of the bromine. And the reason that is going to refer to that is because oxygen isn't going to be different, right? 8 just means contains oxygen in the ion. So it's a 3 in Roman numerals. Roman numerals brackets always means positive. It never means a -3. Bromine can't be -3 anyway. Can't gain 3 electrons. And so I was just working out how many oxygens there are. Well, each oxygen is -2. So I am just going to make an ion with a charge that has to be negative because bromate means negative charge. So how many oxygens do I need to add to +3 to make it negative? 2. 2 lots of those will give me -4, and that will work. In this case, it's multiple choice anyway, so all I needed to do was work out the oxidation state of the bromine. So the second option is potassium bromate 5, because there's 3 oxygens -6. Potassium is +1. Bromine must be +5. The third one down is absolute nonsense because that would be like +3 -2 That would make my bromine negative. You never have like two negative things in a compound. You might have two positive things, never two negative things, unless they are separate ions, but that's not oxidation states. And K3Br, again, that would mean that bromine would have a -3 charge. That's not going to happen. So when it comes to negative oxidation states, it's exactly like you learned it at GCSE, right? Group 7, -1, group 6, -2, group 5, -3. Um, when it comes to positive oxidation states, there's a range because it depends how many bonds we made. Okay, also had a question about the Hess cycle one. It's quite a challenging Hess cycle question in yesterday's exam question example. So that I want to draw a little bit of parallel with a more normal type of Hess cycle or enthalpy changes question, which is where we use combustion. And those of you that were on the year 13 course this week, I think we did this example, where we want to find the enthalpy of formation of methane. So I like write an equation for that. And then we use enthalpy of combustion. So I've got enthalpy of combustion values. And enthalpy of combustion means I'm adding oxygen, obviously, and making carbon dioxide and water. So down the bottom, we would put our products going down. And I'm actually adding oxygen, but we don't normally write that, or sometimes we write it over the arrows, but it cancels out. Oh, it's got a link come up. So we're adding the oxygen, and we've got an enthalpy change, and we can add it all up, and then we can find the enthalpy change here. And the way that a lot of people have been taught to do that is to go this way round your Hess cycle. And if we call that delta H2 and that delta H3, then I'm just going to rearrange it. I'm going with the delta H2. I'm going against the delta H3. So delta H1 is equal to delta H2 without changing the sign minus delta H3. So can you give me a thumbs up? Because I know, Shayla, you asked a question about this. I think it was you. If that makes sense, that using the combustion Hess cycle. Cool. So the one that we did here, a lot more involved. Okay. Here, it's a adding water, so like a hydrated salt situation, which is very difficult to measure because it's when you add water to copper sulfate, it's a little bit exothermic, but it's not so exothermic that you could put it under a beaker and heat it water with it. So it's not like a fire. And you can't just put it in a solution and warm some water up because you only are allowed to add a tiny bit. So we're doing it indirectly by dissolving copper sulfate. And I think most people are okay with working out the enthalpy change for delta H3. I better find the one that I did earlier, right? Because you don't want to watch me do that. So that's your just energy change, mass, specific heat capacity, change in temperature, moles of copper sulfate, and we end up with delta H3 equaling plus 13.5. So I think the more tricky bit of that question is why are we rearranging it like we are? Well, because if I were to relate these three different equations, 1, 2, and 3, this is the one that's going across the top. This is the one I'm trying to find. So this is my indirect chemical change that I can't really measure properly because I can't just stick a thermometer in it. There's 5 H2Os. And then in reaction number 2, in delta H2, I'm adding excess water. So I'm going to add H2O. So this is like combustion. Well, it's not like combustion. Completely different reaction. But the idea is I'm taking that thing on that side and I'm adding water to it, and I'm taking this thing on this side and I'm also dissolving it. And I'm measuring these two energy changes. So the arrows go down because they're just reaction arrows. They're just these arrows here. They go from solid copper sulfate, which is here, to copper sulfate aqueous. So both reactions 2 and 3 have aqueous copper sulfate in common. And so that's my minus 64.5. And then this one is my plus 13.5 that we worked out in the question. And that's because I'm going from hydrated copper sulfate to the solution. And so when I rearrange it, this is the one that I want. I'm going with that, but I'm going the opposite direction to that energy change. So I'm going to switch the sign or take it away. So my delta H is going to be minus 64.5 minus plus 13.5. Sometimes I like to put my energy changes in brackets, so I know that that's the number. And then the minus is what I'm doing with those energy changes. So I'm reversing that because I'm going against it. Does that make a bit more sense? So most of the things that we do that are not normal Hess cycles, anything that looks a bit weird, what we're normally doing is reacting the same chemical, or in this case, doing the same thing, water, dissolving, to both sides of a chemical equation. Other examples, burning both sides, or adding acid to both sides. So sometimes you get like two different compounds on either side which can react with acid, and you can add them to both sides. Get the same salt plus water. Does that make sense? Sorry, my ice cubes are jingling away. Perfect. And again, pop in the chat if you've got anything else, because I've got some other things that people have asked me about over email that I'm just gonna talk through how to do. It might be that you haven't got to these questions yet because we've had a busy few days. So titration, well, this isn't really a titration calculation. This is more like a sneaky dilution calculation, actually. So let's talk through how we get this answer. Not that I've shown the answer here. Actually, I just screenshotted the question. So my calculation questions are quite tricky. There's a lot of things that you would have to actually perhaps write out and work out. And I did that on purpose. It is 0.33. Nice. I did that on purpose because often in an exam, you do have to write things down and work things out for multiple choice. And a lot of students just kind of think that they can just, get the right answer and just go for it without that. So H2SO4 is sulfuric acid. So that's reacting with sodium hydroxide. So because that's two hydrogen ions, that is a 2-to-1 ratio. We're going to make 2 lots of H2O. And the thing that we actually want to know about, Na2SO4. So getting that balance equation right is key to part of this, because the question is about the concentration of the sodium sulfate. So I can do this by straight moles. That works quite nicely. So 25, but it's 25 centimeter cubed divided by 1,000 times by 1. So there's 0.025 moles of that and 0.05 moles of that. That's important to just check that it's not a cheeky limiting reagent question, because there are some of those where like one of them doesn't all react. This is a perfect ratio, so 0.025 and 0.05, they'll all react. And I will make 0.025 moles of that in my product. So that's just using the molar ratio. The concentration, I think we're all year 13 here, so we can use the concentration square brackets of Na2SO4 is 0.025 over the volume, which is now 75 centimeter cubed, because I mixed two solutions together. So 0.075, and it's going to be that one there, 0.33. You could almost visualize that depending on how much you love maths. Okay, because you could just go, okay, it's 0.025 moles. I can see that because I can see that they're like in the right ratio to react. And if it's 0.025 moles over, and now it's in 75 centimeter cubed, basically I've taken that 1 mole per dm cubed solution and I've diluted it 3 times because I've added 50 to 25. But there's nothing wrong with doing it the moles way. Also, watch out for really cheeky questions that say things like, what's the concentration of sodium ions? So, since you're here, you don't want to just be listening to me talk all the time. In the chat, what is the concentration of Na plus in that solution? The one that we've just worked out, the concentration of Na2SO4. What would we end up getting? Because this is also really useful when you're doing like pH calculations. Going from the concentration of a compound to the concentration of an individual ion is a really important skill. Go on, you can put it in the chat, no one will see. You don't need a calculator. I don't think, anyway. There's even one of the answers there as well. So, no one going for it? Really? Take that. Oh, you're trying. Okay. So take that formula, Na2SO4. When you dissolve it, you know what happens to H2SO4. You've written that a lot because it's a strong acid, but this is an ionic compound. So when it dissolves, again, think of like maybe when you're doing lattice energy, and actually, it depends. Yeah. When you're in year 13, you do a lot of these breaking up of ions because you do it for Born-Haber cycles and dissolving. This is what you're going to get, right? So SO4 2 minus. So we haven't changed anything about the concentration of this is 0.33. So now we're just using moles and the balanced equation that when that breaks up into separate pieces, I'll have 0.33 mole per dm cubed of that one. I'll have 0.66 moles per dm cubed of that one. Maybe 0.67, I haven't actually. There you go. Yeah, absolutely. It's just twice as much. Where that's more important is, for example, finding the pH of that H2SO4 at the start, where the H2SO4 splits up into 2H plus and SO4 2 minus. Okay. Actually, I had a teacher ask me how to do this. So she saw it on Instagram and then she was like, oh, she didn't see the question on Instagram, like on one of my posts, and was like, well, how do you fill in the table? And got a bit confused by this question. So I apologize to those of you who, well, actually, I don't apologize if you were here for my course on Tuesday and Wednesday. We actually already went through this, but I do think it's quite a challenging table. So I feel like we could go for it again. There's never too much rates equation stuff. Okay, so values of relative initial rate, blah, blah, blah. We have a rate equation, so we actually know what the orders are. Normally, we have the numbers in the table, and then we go backwards and look at what happens to rate, and we work out the orders. This, if you're in year 12, this does not apply to you yet, although I had a year 12 ask me about this yesterday, so some people are doing that part of the rates topic already if they're in year 12. So it's 0 order with respect to A. So in my first row, nothing changes for these two. So they won't affect the rate. only this one changes. This one is zero order, so that won't affect the rate, and my rate will still be 1. So that's an easy mark, and then it just gets a little bit more of a thinker as we go through it. On the next one, I'm going to compare the first and the third. Relative initial rate, just doesn't really matter that it says relative. We don't care what the units are. We just want to think about what am I timesing it by. So obviously A, we can just ignore completely. It doesn't have any effect. What we're trying to find out is what was the concentration of B. Now we could, in fact, I'm going to show it a different way to what I showed. We could just work out the rate constant, or at least a value that we could substitute for the rate constant. So if I take the first row, and I'm going to take that row because I know everything's right in that row, that was given to me in the question, and just substitute in, the rate is 1, there is K, concentration of B is that. So I'm going to do 0.2 squared times 0.1. I don't know why I use square brackets. That's a weird thing to do because square brackets means concentration. So I'm going to put that in. 0.2 squared times 0.1 gives me 4 times 10 to the minus 3. Do 1 over that. That tells me that K is equal to 250. So I can now put 250 into the rate equation and work out what B would be. So the rate is 0.64. K is 250. B squared, that's the thing I don't know, and that is 0.1. So if I put all of that in and divide by 0.1 and move all that to the other side, I get B squared is 0.0256, and then I can square root my answer, and I get the concentration as 0.16. The other way that we showed how to do it, the quicker way to do it, is just to go, well, what happened to the rate from the first one to that one? It got multiplied by more 0.64. The rate got 0.64 times bigger. I know it's not bigger, but that's what we times it by. The rate is proportional to B squared. So if I times that by 0.64, I must have times that by the square root of 0.64, which is 0.8. 0.8 times 0.2. That gives me the answer. I'll leave the other one blank. Okay, so because I got some other questions as well. Any more questions in the chat, by the way, guys, about any chemistry at all? I'm quite happy. There's quite a lot of calculations-based questions, but if you want to completely sidetrack, well, we have been looking at inorganic, physical, and calculations for the first 3 days, so that makes sense. Okay, percentage yield. Again, it was a kind of case of, I think we learn how to do something, and then when we have to write the equation the other way around, that's when things go wrong. So use that substitution method. Write something down, put the numbers in, percentage yield, is actual mass that you get over theoretical maximum mass. I'm just going to write maximum mass times 100. So, I know the 15. 15, and I know the actual mass, 5.52, and I know 100. So that's the maximum mass of ethanol down here. So I do a bit of a rearrange, put that up there, put that down there. Maximum mass is going to be 5.52 times 100 over 15. I basically divided it by 15%, if you prefer to think of it that way. And I'm going to get 36.8 grams. That's of glucose. Oh, sorry, that's not of glucose, that's of ethanol. So now I am just using moles, just the same as if the question said, what mass of glucose do you need to make 36.8 grams of glucose? Divide that by the MR of glucose, sorry, of ethanol, then divide it by 2 to get the moles, and times it by the mass. I think 72 is the answer. Let's just check. 36.8. The MR of ethanol is 46. That's 0.8 moles of ethanol. It's a 2-to-1 ratio. 0.84 moles of glucose. And the MR of glucose is 180. And so it is 72. Yeah, I was just checking I ticked the right one. I didn't want people to go back to it and go, that looked like the wrong thing highlighted. Okay. What other questions do we have, guys? It's all very quiet out there. Did we do spotting the errors on the Bourne Harbour cycle? Because I didn't put the answers up. So I also thought I would leave a bit of space in the Q&A to do that as well. So I have got how many errors? How many errors can you see on this? Oh, confused on the CL bit. I'm not surprised because I mean there was some errors all over the place. All right. So in a Bourne Harbour cycle, let's look at what's right and let's look at what is wrong. So I think I'll do that cheesy little teacher thing where if it's right, I shall use green, and if it's wrong, I'll use a more reddy colour. Actually, it's not good for the colourblind, is it? Let's go for blue for right, pale blue. So at the bottom, ClCl2, that is correct. We should always have a nice. So I'm going to look through the levels first. Some people I know really struggling with Bourne Harbour cycles, and part of it I think is you don't really understand what the arrows and the lines mean. So if I was to take enthalpy of formation of calcium chloride, the equation would be Ca solid plus Cl2, whoops, gas, like standard elements in standard states to CaCl2 solid. So the lines on the Bourne Harbour cycle, the levels, energy levels, are just either the reactants or the products of a chemical change. And then the arrows are just the reaction arrows. So they go in the directions they go in because they are particular reactions. So I've given a little bit of a clue there. The balancing is wrong on this first line. So there should not be a half Cl2. We're only going to do that if there is one atom in the compound. So for example, NaCl, we would have to have Na solid plus 1/2 Cl2. Or there was a nasty little sodium oxide one in a recent exam paper. That would be, because you're making Na2O, you'd need 2 of those. So just balancing. Your diatomic thing, Cl2O2, should be usually either 1 mole of it or half a mole. Okay. Then let's have a look at the next. Let's have a look at the levels and the descriptions at the same time. I've already gone off my whole like color coding thing, but never mind. These two should be switched around. So that thing down the bottom left should be enthalpy of formation, standard enthalpy of formation, i.e. normal elements as you find them, calcium and chlorine, going to calcium chloride in its standard state. So this is lattice enthalpy. Lattice enthalpy can go up or down, and sometimes we call it enthalpy of formation, and sometimes we call it enthalpy of dissociation, depending how we're using it. It is just whether it's a positive or negative value, whether we start with the ions and make bonds, or whether we start with a compound and break the bonds. Normally, in a lattice energy diagram, the Born-Haber cycle, we have a downward arrow, and we're looking at forming a lattice. But of course, that means the word formation comes into it. Sometimes we call it association instead. Depends on your exam board. So the gas ions are correct. That's all nice. So you should definitely be forming it from gaseous ions. And then we've got all the individual changes going up and down the other side. So atomization of calcium, that is normally what we do next. Let's just check. Have we atomized calcium? Uh-oh, no, we haven't. That should be a gas there. Cl2 is correct. It was wrong underneath, but it should be a whole mole of Cl2 to make CaCl2. Atomization of chlorine, that's a correct label, nothing wrong with that. In fact, it's very good practice to not just write delta H atomization, but tell me what you're atomizing. And then we should have a 2 in front there. You might think, don't be silly, who's going to put a 2 on one level and not put it on the other? Oh, hundreds of people, absolutely hundreds of thousands of people do that all the time. Put like the number correct on one line and then it disappears the next. So follow it round and make sure that what you're doing matches the level below in terms of balancing. Same as a Hess cycle. They are parts of equations. They all link to each other. You shouldn't be losing moles and gaining moles. Calcium gas, and now what we've done with the atomization is we've taken Cl2 and broken it into 2 chlorine atoms. I nearly put a radical thing in. They are radicals. We don't tend to put that in as a Born-Haber cycle. Then we're going to have a first ionization energy, preferably of calcium, although that's not so bad. And then it's the balancing issue again. So there's nothing wrong with, you've got your first ionization energy, you've made Ca+, it's a gas, that's all correct, but it's not balanced because if I was writing an equation for first ionization energy for calcium, it would be Ca gas, arrow, Ca plus gas, plus an electron. You've got to balance it. It's like a half equation. So we need to have an electron here, because if we're showing that that level is taking an electron away, they can't just disappear and come back. So I've got to balance it and make sure that it's still there. And now there's 2 because I've done the second ionization energy and I've made it a Ca2+. So that is all correct in terms of labels. On the top, it is not correct because I've made my chlorine negative too quickly, and that should just be 2Cl gas. This is electron affinity. If I was being fussy, I would rather see it called first electron affinity of chlorine, and it's times 2. If you're doing a calculation, I was going to put a little calculation in as well, but that is where people go wrong, forgetting that that is times 2. The atomization down the bottom is times 2 as well. So I would need to make sure I balanced all of that. I think we've caught them all. So everything after the first 2 rows should be gas, 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 single atoms, no 2s anywhere. Don't want to see Cl2 minus. That's not really a thing, not something that we'd come across anyway. And then make sure that you get the difference between lattice enthalpy of formation and just enthalpy of formation, which is just making a compound. Have I done? Yeah, I have. Okay. I've gone through everything that anyone asked me to go through specifically. I don't mind spending a few minutes more if anyone's got anything else. Or it might be just as well for anyone who's watching, catching up to explain what I'm going to do on Sunday. as well as any more Q&A stuff, is prize draw. I'll do that at the end of Sunday's Q&A. And what I'll do is I'm actually just looking at like how much people have done on the course. I'm not obviously grading it. I'm not looking at what you've achieved in a quiz. Um, and so therefore, I'm just gonna go through like how much people have done, and then I will put everyone's names in a hat. It may be a virtual hat, but I will try and make it a real one. So, and basically, the more people have done and interacted, especially the people that are here live now, you get more names. So you just get more chance. Um, you're in year 12, can you go over back titrations and calculations? Yes, I can, but can we leave it for Sunday, else? Is that all right? Um, Especially if you've got a particular example one, perfect. And if you, not that I'm plugging my slightly weak in subscribers YouTube channel, but there is a video on back titrations on there. But yes, I think I put like a nasty example, didn't I, in the exam question practice. So we can go through that on Sunday. That'll be a bit more of a awake time to be going through that. I think we're all a bit tired on a Friday afternoon. Perfect. Right. Well done for turning up, guys. And if you're watching it on the recording as well, yes, keep working on the calculation booklet. It's hard work. I'll see you Sunday, hopefully. Have a lovely weekend up until then. Bye bye, everyone.